So this is a lesson about similarities in right triangles. Primarily what we're going to do is we're going to take a right triangle, so triangle ABC, and we're going to draw the altitude from the right angle down to the hypotenuse. So that's this line right here. As soon as you drop the altitude in a right triangle, essentially you create three triangles. Right? You've got the main triangle, ABC, that's one, and then you create this smaller triangle, ACD, that's another one, and then you create your smaller triangle, CBD. And these triangles are all similar to each other, and it's a little bit hard to see, but basically what we're saying is that the hypotenuse of this triangle is in proportion to the hypotenuse of this triangle, and that's in proportion to the hypotenuse of this triangle. And similarly, all the short sides, the shortest leg of all three triangles, are all in ratio to each other. And also, of course, if they're similar, then the longer leg of all three triangles are all in proportional to each other. And it is a little bit hard to see in this picture because the triangles are in all these sort of weird orientations, right? One of the things that can make it easier to see that you have three similar triangles is to rotate the two triangles around, right? So if you take this triangle right here, you can rotate it into this shape so that it now has the same orientation as the original triangle you were working with, right? Same thing with this guy. Take this little triangle over here and rotate it around so that it has the same orientation as your original triangle ABC. As soon as they have the same orientation, then it's easy to see, okay, all the hypotenuses are proportional, right? AB is to AC is to CB. All the short legs are in proportion to each other. BC is to CD is to BD. And of course, all the longest legs are in proportion to each other. AC is to AD is to CB. If we're going to say that triangles are similar, we need to be able to write a similarity statement, right? So the similarity statement, that's this guy, right? So how do we write that similarity statement? Well, it can be really helpful if you notice on the bottom, A, B, A, C, C, B, those are all the first two letters that I wrote down. Those are all the hypotenuses in green. Right? And then what else do we have? Well, we have BC, BC, CD, and BD. Notice that the short leg, the red pieces of all the triangles, those are all the last two letters. And just for good measure, we can check. Is the first and the last letter make up the long leg of the triangle? AC is to AD is to CB. And of course, yes, they're similar, right? So not only do we want to identify these triangles as similar triangles, we should be able to write a similarity statement and compare their proportional parts so that we can write a proportion and solve. So let's take a look at an example. Write a similarity statement and identify the three similar triangles. One of the things that's most helpful in a picture like this is to identify the parts of the triangle. So like in the small triangle here, MN is the short leg. I abbreviated that with SL. QN is the long leg, right? Abbreviated with LL. And then MQ is the hypotenuse of this little triangle, right? So if I'm just looking at this guy, right? Just looking at this triangle right now. So it can be helpful to identify those are the three parts of that triangle. Let's do that for the large triangle, right? In the large triangle, MP is the hypotenuse, MQ is the short leg, and QP is the long leg, right? And then we're going to do this one more time, but we're going to do it for this triangle, right? This sort of medium triangle. We've got QN is the short leg, QP is the hypotenuse, and NP is the long leg. So how does identifying all of the parts of these three triangles help us write a similarity statement? Well, remember in the last slide, we were trying to write the letters in order so that we were writing like the hypotenuse first and then the short leg, so that each time we wrote down the letters, it went in the same order. So we can do the same thing here. Like, let's start with the big triangle, the red one. MQP. Well, what do you notice about MQ, the first two letters? MQ make up the short leg. What do you notice about QP, the last two letters? QP makes up the long leg. So when we write down the other triangles, the little blue triangle and the medium green triangle, we want to write down the letters so that the first two letters make up the short leg and the second two letters make up the long leg, right? So triangle, let's look at the green triangle first. Which two letters make up the short leg in the green triangle? Well, that would be this guy right here. There's the short leg of the green triangle, QN. So we write those down first. Which two letters make up the long leg, right? Well, the long leg in this case is here, NP, right? Let's do the same thing, but now we're going to work with the smallest triangle, the blue triangle. Again, the first two letters are going to be the short leg. The last two letters will be the long leg. So looking in your blue triangle, the smallest triangle here, which two letters make up the short leg? There they are, right? So that would be MN. And then which two letters make up the, oops, let's go back for a minute. Which two letters make up the short leg? That would be MN. And which two letters make up the long leg? That would be N and Q. So we're writing down the letters so that they go in the same relative position as all of the other triangles we're comparing. Now the goal of this is to be able to use these similarity statements, right, so that we can write proportions and solve for missing pieces of the triangle. Okay, let's take a look at this example. Use a proportion from similar triangles to solve for x. One of the things that's going to be most helpful in an example like this is to identify the pieces that we're looking at. So I've labeled them short leg and hypotenuse, and short leg and hypotenuse. The red in this picture identifies the short leg and the hypotenuse of the largest triangle, EGF. And the blue on this picture represents the short leg and the hypotenuse of the medium triangle, GHF. So we can set up a proportion. The hypotenuse is to the short leg as, right? And then the hypotenuse is to the short leg. So these guys right here came from the blue triangle. That's the hypotenuse and the short leg of the blue triangle. And then these guys right here come from the hypotenuse and the short leg of the red triangle, the largest triangle. Now that I have a proportion, I'm going to cross multiply and solve. We'll do the same thing in the second one, right? We're going to identify which two triangles we're working with and then which parts we have. So notice that I have the long leg of the baby triangle, the smallest triangle, and the hypotenuse. So I will also identify the long leg and the hypotenuse of the largest triangle, JLM. That means that my proportion will be comparing the hypotenuse to the long leg, right? So notice that the hypotenuse and the long leg of the largest triangle, the one I have in blue, the hypotenuse is 13, the long leg is 12. If you look at the smallest triangle that I'm working with, right, then the hypotenuse is 5 and the long leg is x. So I'm setting up a proportion where I'm comparing the hypotenuse to the long leg, and then I'm pulling the hypotenuse from both triangles and the long legs from both triangles, setting those into a proportion, cross multiplying and solving. So I get 60 equals 13x, and I get x equals 60 thirteenths. Okay, you're probably thinking to yourself right now that this is kind of hard, right? They're a little bit hard to set up. There's a lot of stuff happening in these pictures. And you're right about that. When you have three triangles and they're all similar to each other, and you're trying to see how they're all the same, like which parts match up to which other parts, it can be really tricky. So in the remainder of this section, we're going to look at two theorems which are shortcuts, which can help us to solve problems just like these two in this example without having to identify specific parts this way. In order to do that, we need to talk a little bit about something called means. Now, an arithmetic mean is something you already know about. Another word for an arithmetic mean is an average, right? So how do you find an average? Well, you add two things together and divide by 2. When you think of an average, it represents a number that's in the middle, right? So here's two numbers, 3 and 9, right? Which number is in the middle of 3 and 9? Well, that's easy, right? 6 is in the middle because it's 3 spaces away from 3 and it's 3 spaces away from 9. What you're doing when you find an arithmetic mean is you're looking for a number which adds repeatedly, right? So instead of 3 plus 9 gives you 12, it's which number could you add repeatedly and get 12? Well, which number plus itself gets 12? Obviously 6. So now we have this idea of a geometric mean. And you'll notice right away that we've got a proportion here, right? A geometric mean of two positive numbers a and b is the positive number x which satisfies this proportion. Now we were talking about proportions and we were saying that proportions had two parts, right? Proportions had something which we called the means, there's the mean right there, and something called the extremes. And what we were saying about the means and the extremes is that the extremes were going to be the biggest number and the smallest number. And the mean was going to be the number that was in the middle. But what do we mean by in the middle? Well, it's a little bit different from an arithmetic mean, right? Because you're going to be multiplying and taking the square root. And it's not going to seem like the middle, but it's a different kind of a middle, right? So you've got two numbers. You've got 2 and you've got 8. Which number is in the middle? Well, this time, instead of meaning which number is in the middle by adding the same thing each time, I mean which number is in the middle because you've multiplied by the same thing each time. In other words, instead of 3 repeatedly adding to itself, we said, well, we multiplied by 2 repeatedly. So instead of having 2 times 8 gives me 16, it's what number can repeat itself and give me 16? Well, of course, that number is 4. So the geometric mean of 2 and 8 is 4. And we would say that it's in the middle multiplicatively. Multiplicatively. This is one of my all-time favorite words, multiplicatively. All right, so what does this have to do with similar triangles in right triangles? Well, we're going to get to that in just a second, but let's practice finding the geometric mean. To find the geometric mean, the best, easiest way to do it is to set up a proportion, right? So 4 and 12 are the extremes, and then x is your mean. So 4 is the smallest number, 12 is the biggest number. Your x, your mean, is in the middle. If you cross multiply, you get 4 times 12 equals x squared. These are easiest to simplify if you don't multiply out 4 times 12. Instead, break 4 times 12 into its smallest pieces, like 4 times 4 times 3, and then take the square root. What's great about this is that you can turn the square root of 4 into something, and this square root of 4 into something, right? And so you get x equals 2 times 2 root 3, and you get x equals 6 root 3. Okay, let's try it again. Let's find the geometric mean of 8 and 14. So set up your proportion. 8 and 14 are your extremes, the smallest and the biggest number. X is your mean, right, in the middle. So cross multiply. Do not bother multiplying 8 times 14. Instead, break everything into pieces and take the square root. So just like last time, right, we're going to do the square root of 4 and the square root of 4. We're going to get x equals 2 times the square root of 7, and we get x equals 4 root 7. All right, last one. Let's find the geometric mean of 15 and 25. Start by setting up your proportion. Those are your extremes. X is your mean. To solve a proportion, we cross multiply. Again, do not bother multiplying 25 times 15 because you're just about to take the square root of it. Instead, take the square root now. This turns into something you already know, right, which is 5. And this becomes x equals 5 root 15. All right, so those two fancy theorems we were talking about are here. And they both use the geometric mean, which is why we had to spend a little bit of time talking about it and practicing to see how it works. So this is called the geometric mean altitude theorem. Sometimes it's called the blip theorem. I know that sounds really weird. We can talk about that later. Why is it called the blip theorem? You might have some teachers calling it that. It has to do with the way it looks when you draw it out. You don't have to call it anything fancy. Here's what they're saying. Because these triangles are similar, the altitude, this guy H right here, he's always the mean of two other pieces. And the two pieces that he's the mean, middle, or average of, multiplicative average of, are the two segments that the hypotenuse is cut into. So these two segments down here, this red segment here, right, this guy is the smallest piece. This guy is the largest piece. Those are your extremes. And then the altitude is going to be your mean. He's going to be in the middle. So we'll set up a proportion and then we should be able to solve. Okay? Okay, let's take a look at it. So that's the blip, right? It goes like a heartbeat monitor. Bleep, bleep. Right? There's the blip. What we're saying here is that x is going to be the geometric mean, that guy right there, the altitude, of the two pieces that make up the hypotenuse, 10 and 14. Set up your proportion, cross multiply to solve, x equals 2 root 10. All right, same thing over here, right? Let's look at B now. Let's set up our blip, 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 like that, like an upside down heart rate monitor. The altitude 6 is the geometric mean of the two segments of the hypotenuse. So put your 6 in there. Put your two pieces of the hypotenuse in there. Cross multiply and solve for A. Okay. So that's the first shortcut theorem we have, called the altitude, geometric mean altitude theorem. The next theorem we're going to look at is the geometric mean in the leg theorem. Okay, this guy's sometimes called the boomerang. This theorem says that you can look at the length of the legs of the right triangle, and it will be the geometric mean of the hypotenuse segment that's closest to it and the entire hypotenuse. Now, it sounds like a mouthful, and this looks really crazy, but let's use some colors. So, this guy over here, B, is a leg of the whole triangle. The leg will serve as the geometric mean. So notice where I put it in the proportion. The extremes will be the adjacent segment of the hypotenuse. So that's the blue guy down here. Okay, so that's this guy. That's going to be one of the extremes. And the other one is going to be the entire hypotenuse. So the red piece, the leg, is the geometric mean of the little bitty piece of the hypotenuse that's closest to that leg and the entire hypotenuse, the blue and the green. Same thing is true if you look at the other leg on the other side. The leg, CB, is going to be the geometric mean of the piece of the hypotenuse closest to him, called the adjacent segment, and the entire hypotenuse. Okay, so the extremes are always the piece of the hypotenuse closest to the leg and the entire hypotenuse, and the means are always the legs. So let's take a look at how we would solve these. This theorem is sometimes called the boomerang theorem, right? You can see there's the boomerang. So the leg, y, is the geometric mean, and the two pieces that make up the extremes are the piece of the hypotenuse closest to the leg, that's the mean, and then the entire hypotenuse. Cross multiply and solve. Same thing on the other side. Let's set up our boomerang. The leg is the geometric mean of the piece closest to the leg, right there, 4, and the entire length of the hypotenuse. So notice that I had to do x plus 4 to find the entire length of the hypotenuse. We're going to cross multiply, and we're going to solve. We get x equals 28.